And welcome back to the workshop dedicated to dispersive hydrodynamics. So I wanted to remind you that there is a small typo in the online program for the workshop. There is no shared discussion between 4:30 and 5:30. We'll have 3 talks in a row. And I also wanted to remind you that the meeting is being recorded and live streamed. So if you do not wish to be recorded, please keep your microphone and camera off and use the chat button for any question. There are also a live transcript, so you can turn this off through clicking on the live transcript button at the bottom of your Zoom screen. And so it's my pleasure to welcome our first speaker for this second session. So Stephane Randoux from Université de Lille, and he will talk about nonlinear propagation in integrable and nearly integrable wave system, some recent experiments and numerical results. So Stephane, the floor is yours.
Thanks a lot, Thibaut. Can you hear me? It's okay?
Yeah, very well.
Okay, thank you. So hello, everyone. First of all, I would like to thank the organizer for inviting me and for giving me the opportunity to present you some recent experimental and numerical results where integrability of the waves is at the core of the observed dynamics. And let me start this talk with something that most of you know. It is Zabowski and Kruskal numerical experiment. The authors have considered the KdV equation with a small epsilon parameter in the dispersive term, and the initial profile, the initial condition is a sine wave. At initial time, the dynamics is dominated by nonlinear effect, and you observe this self-steeping effect. And after some propagation distance, linear and nonlinear effect come into balance, and you observe the generation of a solitonic wave train. So, numerical simulation that has been initially made in 1965, and the corresponding experiment has been made more recently. In this, it has been reported in this PRL paper in 2016, and the quality of the experiment made and of the signal recorded was so good that the author of the experiment have been able to analyze the experiments using IST, periodic IST in this case, because the initial condition is periodic. And they have been able to compute scattering data. And since it is periodic IST, the relevant data is the so-called trace of the monodromy matrix. And you can see here this function close to the wave maker and far from the wave maker. And despite the fact that the two signals are completely different, the two traces are the same. This shows that the isospectrality condition is nearly fulfilled in the experiment, and this demonstrates that an experiment, a water wave experiment, can be close to integrability. Yesterday, you have heard about another water wave experiment. This time, it is not shallow water, but deep water waves. The dynamic is not described by the KdV equation, but by the focusing analysis. And one significant difference between this experiment and the previous one is that the experiments start from the IST. So the first step is to design this discrete spectrum. So you select some discrete point complex plane, one being associated to one solitonic mode, and using some algorithm, you compute the associated solitonic field that is used as initial condition for the wave maker. And there is a set of gauges all along the water tank, and you can observe evolution of the water waves with propagation distance, and also recompute the IST spectrum. And as you can see on these two plots, once again, the isospectrality condition is not perfectly verified. You have some trajectory of the discrete eigenvalue in the complex plane because of the occurrence of a small higher order effect. So these two experiments demonstrate clearly that in water wave experiment, at least, you can synthesize, generate wave field, and also them using IST, or what is often called now nonlinear spectral analysis. So in this experiment, the is of a random nature. So this experiment can be associated to the field of integrable turbulence, which has been introduced by Zakharov in 2009. And so integrable turbulence is the evolution of random wave field and the investigation of statistical properties of random wave field in wave systems that are described by integrable equation. And it happens that this research area can be related to a more applied research area, which is eigenvalue communication, nonlinear eigenvalue communication. As you probably know, fiber optics communication links rely on Fourier theory. So the idea is that you encode the information that you want to transmit inside an optical fiber into Fourier modes. And you don't want any crosstalk between these between two Fourier modes. So nonlinearity is considered as a drawback in this linear communication links. Now there is a change in the paradigm. People try to use nonlinearity, Kerr nonlinearity as an advantage and to encode the information not in Fourier mode, but in the IST spectrum, either in the continuous part of the spectrum or in the discrete part of the spectrum. And also, as most of experimentalists know, you can also, when you have experiment, analyze your data using Fourier analysis, Fourier transform, which is natural base for studying a linear system, but you can also apply Fourier analysis to nonlinear wave system. And once again, there is another view into into data analysis, let's say, which is promoted by the group of Turitin. And the idea is that we can think about applying IST, or what is often called nonlinear Fourier transform, to physical systems, despite the fact that they are not described by integrable equation. And on this plot, you have the IST analysis of wave field measured at the output of the laser. So this is eigenvalue, and trajectories of eigenvalues are different depending on the laser operating mode. So in this talk, I will show you some other example where IST can be used to synthesize or analyze some experimental data. I will start with a box problem. So linear and nonlinear diffraction of a box. Then I will move to some other experiment in optics where we have applied IST tool to analyze data. And at the end of my talk, I will say a few words about results that we had about numerical synthesis of Weather gases. So let's start with a very simple, once again, water wave experiment made in 2017. So it is a one-dimensional tank, and the wave maker generates a wave train, a sinusoidal wave train, with the envelope having a square shape. And we are in a linear propagation regime, so the propagation is governed by this simple linear PDE that you can solve using Fourier theory. And in this theory, the idea is that the phase of the Fourier mode evolve in time according to the dispersion relation, and you can solve this PDE. You can even get some analytical expression. And if you solve this equation, or if you do the experiment, what you will observe is a Fresnel diffraction pattern that is in the field of optics. Now, let's move to the non-linear regime. So we add a cubic nonlinearity to the equation. And now the story is not at all the same as from this numerical simulation of the focusing NLS equation. We do not have a very simple Fresnel diffraction pattern, but a much more complicated pattern with coherent structure which are localized in space and time. However, the NLS equation is an integrable equation. You know from mathematicians that you can solve it using tools of the inverse scattering transform. The way that you can solve this equation can be presented in a similar way as a Fourier theory for solving linear PDEs. The difference is that you don't have a simple Fourier spectrum. You have a more complicated spectrum. You have more complicated spectral data. You have a discrete spectrum composed with discrete eigenvalue and also a continuous spectrum, which is associated to the radiative content. The discrete spectrum is associated to the solid tonic content of your wave field, but you keep the same idea that norming constant and continuous part of the spectrum have their phases evolving trivially in time, like Fourier component in linear Fourier theory. Well, so you know from mathematics that you can solve this equation. Is it helpful to get some understanding in the dynamics that you can see on this picture? If you read books about IST, you will learn that at very long evolution time, what will happen is that the radiative content will separate from the solid tonic content. And if you do some physics, you cannot do much with this because physics deal necessarily with finite time. So it's not very useful. Fortunately, there exists some framework for getting some better insight into the wave dynamics. It is semi-classical framework. To write your NLS equation under this form with this small epsilon parameter in the linear dispersive term. Epsilon is simply the ratio between the nonlinear length and the linear dispersive length. And it has to be much smaller than 1, which means that the experiment is in a strongly nonlinear regime. And you know from semi-classical theories that the solution of the NLS equation can be interpreted in the framework of finite gap theory. And you have different finite gap solutions depending on the position in space and time in this pattern. So for instance, at the early evolution time, the solution in this triangular region is of genus 0, so it's a theta function of genus 0. In these two regions where you have counterpropagating dam break flows that start from the edges of the box, the solution is of genus 1, so it is a conoidal or modulated or solitonic structure. And you have some collision between these counterpropagating dam break flows, which produces a change in the genus, and you get some genus 2 solution of Brazer family. So this is nice because you have some solutions in some mathematical framework. Now the question is that, do we have some spectral signature for this object? And the answer is yes. The spectral signature of all these objects lives in the complex plane. And for genus 0 solution, the spectrum is just composed of 1 band. For genus 1 solution, so noidal waves, the genus is composed of 2 bands, and the soliton has just 2 bands having 0 sizes. Genus 2 solution has a spectrum composed of 3 bands, and all these famous solutions that you know, Akhmedev-Brazer, Kuznetsov-Masoliton, or Peregrine-Brazer, are particular genus 2 solution in the sense that the spectrum lives on the vertical imaginary axis. So these finite gap solutions have simple spectral signature. Can we now measure this at least first in numerical simulation? And the answer to this question is yes. We have developed such a method. So this is a numerical simulation of our box problem for the focusing 1D NLS equation. And we have a look at the wave field at this time equal 10.9. So the wave field here at this particular time is in red. And the question that we ask ourselves is, what is this blue object, the center of the box? What is the genus of this object? So to give an answer to this question, what we have done is decided to truncate this object in this finite region of space. Then we periodize it. So we cut it, we copy it and paste it. And then we compute the spectrum by solving the Zakharov-Shabat eigenvalue problem. And we get this nice spectrum composed of 3 bands, which tell us that this object in the center of the box is indeed a genus 2 solution of the NLS equation. And same thing for another guy at the edge of the box. We truncate, periodize, and we find the spectrum composed of 3 bands. So we have a way to investigate which kind of object we can observe in the evolution dynamics of the non-linear diffraction patterns that we are looking at. So we can go to experimental worlds. And we did some experiments in École Centrale de Nantes in France, where they have a water tank which is 140 meters long, the width is 5 meters, and the water depth was 3 meters. So the first experimental run that we did consisted in taking a very wide box. The duration of the box is something like 150 seconds. The nonlinearity was relatively high. The steepness was 0.2 approximately. And you can see that after propagation distance of 50 meters in the tank, we have disintegration of the box as a result of Benjamin-Fair instability or modulational instability. You have amplification of a small noise surrounding the plane wave background, and the box is destroyed at long evolution distance. So in the second run that we did, we have decided to first decrease the steepness and then to generate three boxes. The first one has a duration of 30 seconds, the second one 45, and the last one has a duration of 60 seconds. And you can immediately see that we do not see the same dynamics at all. There is no Benjamin-Fair instability. And we see this nice dynamics with counter-propagating dam break flow starting from the edge of the box and colliding in the center. And this experiment is placed in the nonlinear regime. So this epsilon parameter is small in our experiment. So we can now investigate the validity of the results that we get from semi-classical approach and theory. First thing that we do is to check what is named breaking line. So this is line separating the region where the solution is of genus 0, plane wave, from the region where the solution is genus 1, so modulated cnoidal wave. And you can see that this theoretical result works quantitatively well without any adjustment of any parameter. And also the mathematical solution is now in this region where the solution is of genus 1. It is this modulated cnoidal waves, and once again without any adjustment of parameter, we have a good quantitative agreement between the modulated cnoidal wave, the solution, mathematical solution, and what we observe in terms of envelope of the wave field. So well, now we can move to IST. So the box problem is a very well known problem in IST, zero boundary condition. So we even know from the IST the number of discrete eigenvalue which are embedded inside each of two boxes. It just depends on this epsilon parameter, which is a measurement of the strength of nonlinearity. And this simple formula from IST tells you that we should have 3, 5, and 7 eigenvalues, discrete eigenvalues, solitonic modes in each of these three boxes. So we have taken the measured wave field close to the wave maker, and we have computed the IST, the discrete IST spectrum, just by solving this problem. And it happens that analyzing the experimental signal, we find 3, 5, and 7 eigenvalue close to the wave maker. And we did the same, but far from the wave maker, so at a distance of 120 meters. And as you can see, we still find 3, 5, and 7 eigenvalue. You can see that the isospectrality condition is not perfectly fulfilled because you see that one eigenvalue is drifting on the right, same thing there. So, okay, we keep the same number of eigenvalue, but the isospectrality condition is not exactly fulfilled like in a numerical simulation, but this is due to a small and perturbative higher order effect, but the experiment is quite reasonably well described by an integrable dynamics. Now we can move to the question of can we identify the genus of the nonlinear objects that emerge in this nonlinear diffraction problem. So we have increased a bit, I think, the steepness in this experiment. I will talk only about the central box that we have there. So this is a wet field measured close to the wave maker, and as you can see, we have 6 or 7, maybe 7 eigenvalues there because we have increased the steepness. It was 5 in the more linear regime before. So this is close to the wave maker. And far from the wave maker, we have this strong oscillation that we measure there. And we have 6 eigenvalues with now some velocity. You have a real part to the eigenvalues. So we have lost 1 eigenvalue. because the dynamics is not strictly integrable. Well, anyway, let's try to do this local IST analysis. So let's consider this red guy that we measure there. And let's do our IST analysis. And what we do from this is two main bands far from the real axis and one smaller perturbative band. So this tells us that this object is close to a genus 1 solution of the NLS equation. And for the central guys that we measure here in the central part of the box, we do the same local IST analysis to get this nice spectrum with 3 bands, which tell us that the objects that emerge as a result of the collision between the dam break flows is a genus 2 solution of the NLS equation here locally in space and time. So we have recently applied the same tools, not in the context of water wave experiment, but in the context of optical fiber experiment. So this is a space-time plot that you probably know. It is destabilization by a small noise of a plane wave. So here it is numerical simulation, but we did the experiment. So this is our initial condition in the experiment. The experiment have been made by Alexandre Lebel and other colleagues in Lille. And using what we call time-length system, we have been able to measure the amplitude and the phase of the brazier-like structures that emerge after destabilization of the plane wave. So we look at this region of the measurement that we did. And these yellow guys that we isolate, where we measure the amplitude, the intensity, and the phase, we can do the IST analysis of this, and we get this spectrum composed of 3 bands, which tell us that this object is locally in space and time, a genus 2 solution of the NLS equation, so Blazer solution. And same thing for all neighbors. So this green guy here has this spectrum here in green, and the other one has another spectrum, but all of them are mostly composed of 3 bands. Then another interesting thing that we did was to make the IST analysis of a famous experiment. Hamid said a few words about this experiment in his talk just before. So in this experiment, a peregrine brazier is generated by taking a plane wave and perturbating it using a small perturbation of amplitude epsilon and having a wave vector k naught. So in experiment, this means that you take a strong laser field and another perturbative one, which is frequency detuned with respect with the first laser. So if you take this problem and make the IST analysis of the wave field, if the amplitude of the sideband that you put is small, so let's say 10 to the power of -2, then you will get this spectrum composed of a main band and 2 smaller bands. This spectrum is not very far from the spectrum of a peregrine soliton, so everything is fine if the amplitude of the sideband is weak. Now, in the experiment, they did not use such a small amplitude because they wanted to observe a large peak at the output of the fiber, so over a given propagation distance. So they had to increase the amplitude of the small sideband, so the power of the second laser, in order to get this large peak of the output of the fiber. But if you do this, the IST tells you that you change the genus of the solution, and instead of having an object having a spectrum composed of 3 bands, a genus 2 thing, then you have a genus 4 object. So according to IST, this object measured in this experiment is the genus 4 solution of the NLS. And if you want some more detail about the work that we did on this subject, you can find it in this PRE paper. Now I move to the last part of my talk. So yesterday you have heard about this experiment where we have generated a soliton gas. So the experiment starts from the IST. So we have designed a wave field having a strong solitonic content, and all the eigenvalues are densely placed in some limited area of the complex plane, and we have been able to observe this nice evolution dynamics and measure also the density of state of the soliton gas. Now, you probably know that there are some recent theory developed by Gennady and also Alexander Tovbis, spectral theory of soliton and Brazer gases. So it is theory made within the framework of finite gap theory. So I think that Alex will say more about this in his talk just later. So if I simplify, maybe oversimplify, but let's do this. What is the difference between soliton and Brazer gases? Soliton gas is an ensemble of discrete eigenvalues in the complex plane for the focusing endless equation. A Brazer gas can be seen as an ensemble of discrete eigenvalues in the complex plane and a branch cut associated to the plane wave content. And the question that we had is, can we get some evidence of this object, a Brazer gas, first in numerics? And what we did was that we used Darboux transform as a mathematical method to construct the gas. So Darboux transform is an iterative process where you start from a solution of the NLS equation. In our case, it was a plane wave, and you iteratively add some discrete eigenvalue. And since we wanted to observe Brazer gas, we had to add many of these discrete eigenvalues, typically 50, and to do this we had to implement arbitrary precision calculation, otherwise we don't get the solution. And what we get if we do this numerics is this kind of space-time plot. So the left column shows you a generic Brazer gas. You have an ensemble of 50 eigenvalues in this region of the upper complex plane. You have the branch cut, and you can observe that the dynamics of the Brazer gas is highly complicated. You can think about building Kuznetsov-Mohr or Akhmediev Brazer gases just by putting a dense ensemble of eigenvalue either above or inside the branch cut, and you will observe Kuznetsov-Mohr or Akhmediev Brazer gas. And if you put this dense set of points exactly at the end point of the branch cut, then you will get peregrine Brazer gas. Then we have made some other numerical experiment where we have propagated a generic Tajiri-Watanabe Brazer inside some Brazer gases. Here it is Kuznetsov-Mohr Brazer gas. This additional Brazer is parameterized by this blue eigenvalue that you can see there, and the Brazer gas has a dense set of eigenvalue located in this spectral region. And you can see that this Tajiri-Watanabe Brazer collide with the Brazer gas. Each time that there is a collision between the Tajiri-Watanabe trial Brazer and one element of the gas, there is a space shift, and at the end it can accumulate, and you have a macroscopic space shift. And we can compare the values that we get from numerics from spectral theory of Brazer gases derived by Gennady and Alex. I think that Alex, of course, will talk more about this. And there is a very good poster by Giacomo that you can see in the poster session if you are interested by this nice topic. So I think that I have finished. I would like to thank you for your attention and also acknowledge many collaborators who have been involved either in experiment or numerics, and also discussion about theoretical things. So I will not give the name of everybody, but some optical fiber experiments that I presented today have been made by Alexandre Lebel in Lille. Also, we have collaboration since many years with Gennady. Giacomo will present this poster on Brazer gases. I would like to thank Amin Shamshub and also Bertrand Kieber for providing some data which have permitted us to do some IST analysis, and also more water wave people from Nantes, Félicien Bonnefoy, Guillaume Ducrozet, and also Eric Falcon for giving us access to this nice facility where we did some water wave experiments. So thanks again for your attention, and if you have any question, I would be happy to try to answer.
Thank you, Stephane. Thank you very much. So do we have any question? We have time for some question. So either unmute your microphone or write it in the chat.
I may have a question.
Go on, Rémi.
Thank you very much for your talk. I may have a very naive question, which is if you can do some transport experiment of a special solution into the Brazer gas or even into the soliton gas, does it make sense then to look at the properties of the gas? I'm thinking about compressibility and other. This might be a very stupid question, sorry.
No, I'm not sure that I get the question, but transport of one solution, can you clarify what you mean by transport?
Right, so if you go to the last slide. So, I mean, maybe this is completely wrong, but I'm willing to interpret this as sort of a transport of a particle inside a gas.
Yeah.
And this kind of measurement, could you, through this kind of measurement, could you access some sort of properties of the gas like compressibility or?
You can, doing this experiment, you can check validity of kinetic theory of gases. So this is what we did. So the spaceship that is accumulated by the trial Brazer is determined by the density of state of the Brazer gas, and this we can check.
Okay, thank you. Thank you very
much. Can I make a quick comment about this?
Yes, yes, go on, Benjamin. Yeah.
Thank you, sorry. Yeah, so I think related to that, so maybe you could even measure dynamical correlations, because this is related to the transport coefficient of the previous question. So could you measure correlations between, like you do a little perturbation at some initial time and then see what happened at a later time and look at the correlation with some observable at a different position? That will be related, for instance, to the HYDW weight, which is a property of transport of gases in general. And I'm sure if you could measure these things here.
Okay. I think that we need to discuss, because I'm not sure that I get the point.
Yeah, well, yeah, we can discuss later in the discussion session. Sorry. Thanks.
Okay, thank you. Sorry.
Okay.
Do I have a time for a small question?
Yeah, Andre, for a small question. Yeah.
Yeah. Oh, thank you. Stephane, I have a question about this localized T procedure. Am I right that when you do that and when you want to identify the genius of the solution in some region, you have to catch the biggest period of the wave field? So let me explain what I mean. Imagine you have, for example, two periods in the solution. At the center, you have some kind of wave field, and you think that there is a genius like M, right? And then imagine you have two characteristic periods, a smaller one and a bigger one. And if you catch a smaller one and then you do periodization, then you, I guess, lose some structures from the bigger period, and then you get smaller genius than you should get. I mean, for example, if there would be different a number of different solitons, if you think about this problem like in solitonic language, then you simply miss some solitons if you take a smaller period. So.
Yeah. My answer to this question is that it is there is no theorem. It's just empirical procedures that we implemented, and it is local thing. And in many examples that we have tried, so this idea to isolate reasonably well some structure and to truncate and then periodize gives us something that we can connect somehow to semi-classical theory. So it works for this box problem. It works also for large hump and regularization of gradient catastrophe, so peregrine soliton. It works in this kind of scenario. So it's empirical thing, and it works for one single structure that you isolate, truncate, in many examples that we did.
Yeah, I just looking at this picture, and I see that there is a smaller peak and a larger peak, and I can imagine if you take a larger period, like on the left top picture, if you take a larger period, you will catch an additional.
Sure, you're right. So if you take two peaks instead of one, then you add some additional modes, and then you will see additional bands in the spectrum, and then you will interpret
the genius
as being a higher genus solution of the NLS equation.
And the theoretical result about the genius, it was about local genius.
Yeah.
Okay, it was about local genius. Okay,
it's a local thing. The idea is from discussion with Gennady, and it comes from the idea that I think Gennady can comment maybe on this. In this downbreak problem, you have a modulated noidal wave, and you have a slow modulation of the solution. And the idea was to isolate each guy and to see if we can get the genus. But if we talk about the noidal waves that we have in this part, the modulus of the solution changes slowly with the space, and this we can also see it using our procedure because we have a slow modulation of the band structure of the solution.
Okay, thank you.
Okay, maybe if we have other comments, we can do it for the free discussion. So there is a comment from Peter Miller in the chat that also most multi-phase solutions are not periodic at all. So I think it was for the previous question. But okay, maybe let's do this during the free discussion.